Alright, so this is the bungee assessment. In this situation, we have a guy bungee jumping down a cliff. His mass is 75 kilograms. The spring constant of the bungee cord is 75 newtons per meter. The rest length of the bungee cord is 40 meters. The first question we have is, well, before we deal with the questions, as this guy goes down, I'm going to identify four kind of important points. The first one is A, where he's just chilling up at the top here. The next one is going to be when he jumps off and he gets to the point, the bungee is going to be slack, 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 and then once it gets to a rest length, it's going to start stretching out. So that stretch point is going to be B. Then as the bungee cord stretches out, he starts to accelerate in the up direction. He's decelerating down. And eventually he's going to get to a point where his acceleration is no longer going to be down and it's going to be start to being up, which is a little bit after B, and we'll call it C. And then we have the point where the bungee is at its maximum stretch distance, which we'll call D. So the first question we have here is, how far is the guy going to fall before they come to a stop? And the way we're going to deal with this is using the energy concept. We know that the energy when he starts falling at A is going to be equal to the energy when he stops falling at D, when he comes to a stop. And we know that the energy at A is all gravitational potential energy, or UG, and the energy at D is all going to be spring energy, potential spring energy, which is US. And we can write this as mgh equals 1/2 kx squared. And now we can just start plugging. Our problem here is that we don't know what the stretch distance x is going to be at D, and we don't know what the total height that he's going to fall is. So we need some kind of an equation to relate these two variables. Well, what we can do is we can look at the bottom of the bungee as h equals 0. And then we can look at his height above from that. So we know that when at B, his height is going to be, his height is going to be a function of the stretch distance. So we know that his height is going to be x, the total stretch distance, minus 40. Or actually, his height's going to be the stretch distance plus 40, right? Because he's going to start stretching at B. So it's going to be x plus 40. And we can rearrange this to solve for x by saying that x is going to equal h minus 40. Because our stretch distance is going to be the total distance, the total height, minus that 40 part. So we're going to plug in mgh. Oh, the interesting thing is that since m and k are the same number on both sides of the equation, we can cancel it out. So that's just a nice thing about this problem. So we'll get gh equals 1/2, and now we're going to substitute in our x, h minus 40 squared. So now we'll plug in g of 10, 10h equals 1/2 h minus 40 squared, and move the half over, 20h. Now let's factor this out. We'll get h squared minus 80h plus 1600. And then move the 20 over. 0 equals h squared minus 100h plus 1600. And as we factor this, we'll get h minus, because 20 and 80 both go into 1600, we'll do h minus 20 and h minus 80, because these two will, 20 and 80 will add to 100. So we'll get h equals 20 and then h equals 80. So one of these we can throw out as just wrong, because we know the total h is going to be at least 40. So we know this one is wrong, and we know that our true h is actually going to be 80 meters. So that's how far he's going to fall before he stops. Our next question is going to ask, where is the guy's maximum acceleration? So we're thinking his acceleration all the way down is going to be 10, because that's just the gravitational constant. But his acceleration when he gets to the bottom, that's probably going to be more than 10. So the maximum acceleration is going to be the maximum stretch. So we know acceleration equals F net over mass. And so our F net relative to mass is probably going to be the greatest at D. So at the bottom, if we draw a force diagram, we have mg is, this arrow is too big. We have mg is going to be 750. And we know the up force is going to be more than that, because he's going to be accelerating up. And it's going to be Fs, or also Kx. And we know K is 75, but X, at the bottom, we just figured out that the total height is going to be 80. Let me write that in just for the reference. And we know our X is always, I think in that last part we had X equals h minus 40, right? And since our height is going to be 80, X will be 80 minus 40, so X will be 40. So our force by the spring is going to be a whole 75 times 40, or 3,000. And we also have a 750 component down, so net force is going to equal 3,000 minus 750, which gives us 2250. And that number over our mass of 75 kgs, that's going to equal 30 meters per second squared. So it turns out it is going to be the greatest at the bottom, his acceleration, because all the other time when he's in free fall it's just 10, and then when he's accelerating, he's moving down but accelerating up as he goes from B to D, but his max acceleration will be at D of 30 meters per second. Our next question is dealing with maximum speed. So this is interesting, because if we think about our speed, he's going to be accelerating this way, accelerating, and his velocity is down, accelerating. It's not just going to be at B, because his net force is still going to be down until the bungee cord pulls up just as much as the earth is pulling him down. So his maximum speed's actually going to be at C when the bungee and the earth balance out the forces on him. So that point is going to be where we have mg and fs, or kx. And we know mg whole time 750. And kx, well, we need to solve for the x. We know because these two are kx and mg are going to be equal, right? So we'll get 75 times x equals 750. So x has to equal 10. Okay, 10 meters. So at his maximum speed, his stretch distance is 10 meters. Now we can use the energy concept to find his speed at sea. So we can go energy A is equal to the energy at C, right? And energy at A is all gravitational potential. And energy at C, we have three components. We have a gravitational potential, because he's not at h of 0. He's at h of 30, right? Because that extra is that extra stretch is 10 meters. It's going to be at 30. So we got that component. We have a kinetic component because he's moving, and we have a spring component because of the bungee cord. So we'll write mgh equals mgh plus 1/2 mv squared plus 1/2 kx squared. As we talked about earlier, our m's and our k's are both the same number, so we can cancel all the m's and all the k's out since we have them on each piece of this puzzle. Now we can just plug and chug. So our GH, we know our H and we know our G is going to be 10 times 80, so 800. That's going to equal our secondary GH, which is going to be a G of 10 still, but a H of 30. So that's going to be 300. Our MV squared is what we're solving for. And our KX, we know our stretch distance is 10, so it's going to be 1/2 times 10 squared. 800 equals 300 plus half v squared plus, this is going to be 100 times a half, gives us 50. Move the numbers to the one side, we'll get 450 equals 1/2 v squared. 900 equals v squared, and we get a v of 30 meters per second as his maximum speed.